Disproving statements. So I'm going to talk to you about these two quantifiers, which you have seen before. So in mathematics, for some reason, if we flip a capital A upside down, it means for all. And if we flip a capital E backwards, it means there exists. I'm not actually aware of many other cases where we do some sort of rotational reflection on common letters to get something, but you're welcome to become a famous mathematician and invent some stuff if you want to. To prove a for all statement, we just need to mathematically demonstrate that it's always true for every case, or perhaps you might mathematically demonstrate that there is one case where it's not true. That would prove that the for all is false if one case doesn't work. And that would be disproving it through counterexample, as I've written there in purple. So just keep that in mind, that's one option. So we're going to do a couple of proof by for alls. One of them is a counterexample type proof, and one of them is a proof for all the whole way. So here is example 8, and I might just zoom out, I've got a little bit of stuff there. So I've got a function, p of n. It's the p function because it represents some primes. And the statement is that p of n equals n squared plus n plus 41. It's a pretty amazing function. Pick a number between 1 and 10 and do that right now in your calculator. And I guarantee you get a prime. It's pretty super duper like that. I'm going to do 9. If I do 9 squared plus 9 plus 41, I get 131, which is a prime number. Anybody else got one? Sorry? 6, what'd you get? 36, 42, 83, prime number. Cool? The good thing is it's pretty easy to prove that you're not going to get even numbers, because if n is even, n squared plus n is even, plus an odd is odd. If n is odd, n squared is odd, and n is odd. Add the two odds together, you get an even, plus an odd, and you've got an odd. So that's a step in the process of proving that all of these numbers are prime. Who's got any other ideas on how we could prove all these numbers are prime? Actually, it's actually quite tough. In fact, this is our disproving for all statement. So this is a for all statement, and therefore all we have to do is show that there is one n which doesn't give us a prime. Can anybody tell me what a value of n which doesn't give us a prime for this function is?
1.
So?
1.
1 squared plus 1 plus 41 is 43, which is prime. And don't say 2. I'm not going to sit here and go through them until we find one. There's an obvious one. It's not that obvious, but it's obvious-ish. 10 squared plus 10 plus 41 is 151, which is prime.
41.
0 squared plus 0 plus 41 is 41, which is prime. 8 squared plus 8 is 72 plus 41 is 113, which is prime.
It's 1,763 prime.
I'm bored. I don't know. Can somebody have a look at this function and think, when will I have a common factor here?
Root.
For what value of n will I definitely get a common factor?
Between 1 and 10.
41.
41.
Whoa.
What if it was 41? What if I say...
It's 1,763 max. Which is prime.
You don't even have to evaluate it. Look at this. P of n, P of 41 is equal to 41 squared plus 41 plus 41, which equals 41 brackets 41 plus 1 plus 1, and that's a composite number. It's got a factor of 41. So by making n, so it actually proves in this case that if you've got a quadratic with a constant term, then there's always going to be a factor at some point. Whatever that constant term, if you substitute that value in, there's always going to be a common factor. So therefore, n equals 41 gives P41 is not prime, and therefore the statement is not true. And I should actually write here, I should have put it in between, and I still can, so I will. That therefore there exists an n in the natural numbers such that Pn is not prime. That's a better way of writing it. That's more elegant. Okay? Any questions on that one? All right, so that is our proof by counterexample. You might get, so the textbook mixes these up. So you might actually have to stop and think, if it's getting too hard to prove it's true, then maybe think through, is there a possible counterexample? There aren't many examples of these types of questions. So really, if you do the textbook questions, you'll find that you get to the point where you can do most of them. And you may have noticed that this is actually, the answer was there. But anyway, counter statement. Example 9, on the other hand, is very similar. Let's say that it is thought that there exists an x in the natural numbers such that p of x equals x squared plus 5x minus 14 is prime. Prove that this is not the case. So what we have to prove now, because we're proving there exists, we have to prove that there does not exist. Even one example. 14. So if you put 14 into that, what do you get? Do you get a prime?
Negative 4.
You don't get a prime. Good. So now you've proven it for 14, but this statement is saying there exists an x value. So they're saying you to do it that way, you'd have to test every single possible x value, every natural number from 0 to infinity. So how might you show that a quadratic expression is always has more factors than one in itself? Like let me show you this. This at the moment, p of x equals 1 times x squared plus 5x minus 14. So it definitely has factors 1 in itself. And what did you say, sorry? Can you factorise this?
Negative 7 and
Plus
2.
7 minus 2.
Plus 7 minus 2. I had to give 5. Multiply to give negative 14. So negative 14. And so we get x plus 7, x minus 2, which means it doesn't matter what x you put into here, it will have 2 composites. It will have 2 factors. I can see a slight issue at the moment, but let's just go with this. Therefore, there does not exist an x. I'm going to change this in a second, so maybe don't write it down just yet, such that p of x is prime because the factors x plus 7 and x minus 2 always exist. So is there any case here where that might not be true though? Because I can see a bit of an issue. What about this? What if x is 3?
X squared is 9 plus 15. 24.
What do you get if x is 3? 10. And what is x plus 7 and x minus 2 if x is 3?
10
And 1. So the x plus 7, x minus 2 aren't actually different factors when x is 3 because x minus 2 gives you 1. So that actually gives you the 1 in itself pair. So you've got to be careful. So we need to look at the special cases. There are cases here. I think we have to say there does not exist an x that is in the natural numbers such that where x is greater than or equal to 4. So if you've got greater than or equal to 4, then you'll have 4 minus 2 or 5 minus 2. You'll get different factors here every time. But this x minus 2 causes the problem because it not only does it create 1 as one of the factors, if x is 3, but it also creates 0 and negatives. So you have to be a little bit careful here. I'm going to test those cases. So the cases are, if x equals 3, then p of x equals 10. Now, x plus 7 and x minus 2 generate the factors 1 and 10, which do not disprove that it's a prime number. But we do know something about 10, don't we? 10 is not prime. Because 10 is 5 times 2. Yeah? Now let's check the next case. We have to go down to x equals 0. If x equals 2, then what does p of x equal?
4 plus 10, 14, 0.
Yeah, okay, so we've got 4 plus 10 is 14 minus 14, so we get 0. Is 0 a prime number?
No.
0's not even divisible by itself. So a prime number is divisible by 1 in itself and has exactly 2 factors, which is why 1 is not a prime number because it only has 1 factor. 0 has no factors and also has an infinite number of factors because everything can divide into 0. So it's not defined as prime. The only factor 0 doesn't have is itself. And to be prime, it has to have a factor itself, but you can't divide 0 by 0. That's undefined.
How can you divide something to 0?
How can you what?
You said it has infinite factors because anything can be divided to 0.
No, if it has infinite factors, it means it can be divided by anything. 0 divided by 10 is 0. So it gives you a whole number, or gives you a natural number. If x is equal to 1, p of x is equal to negative 8, and either we go with the definition that prime numbers have to be positive, or we look at this and say, well, negative 8 is equal to negative 2 times 4, which is not prime. So we've done it for that one. And the last one, because we're talking natural numbers, case 4, if x equals 0, p of x equals negative 14, and negative 14 is also equal to negative 2 times 7, so that's not prime. So by factorising, we have shown that p of x is always a composite number for n is greater than or equal to 4, and then we've also shown the other cases. So therefore p of x is always a composite number. The other way you could show that a number is always composite, other than factorising, is if you can prove the expression is always even. If the expression is always even, then unless it equals 2 at some point, 2 is the only even prime number. So prove that it's always even, prove that it's always growing perhaps, and prove that it never equals 2, and you've shown that it's a composite number. So there's your 2 examples for this exercise. That's 8E, ignore 8F. I'll delete that in a second. That's the proof by induction, which we'll do next week. Are there any questions on that?